Good morning, student. Let's start today's class. In today's class, we'll see or we'll discuss about extrinsic semiconductor. In previous classes, we already discussed about intrinsic semiconductor. What is intrinsic semiconductor? The pure form of the semiconductor is called intrinsic semiconductor. There is no impurities are there in the semiconductor. That type of semiconductor is called intrinsic semiconductor. Okay, we also see we will no, we we also see that the process of uh, what process of current flowing through the intrinsic semiconductor. Okay, in today's classes we all discuss about intrinsic semiconductor. Okay, what is intrinsic semiconductor? Sorry, what is extrinsic semiconductor? You know about intrinsic semiconductor. The disadvantage of intrinsic semiconductor, which we improved, which we want to improve in extrinsic semiconductor, is that in the intrinsic semiconductor has little current conduction capability at a room temperature. At a room temperature, there is a little current conduction capacity of intrinsic semiconductor. These disadvantages we want to recover or we want to improve. Okay, this improvement this to achieve high conduction capacity, we should add so small amount of suitable impurity to the semiconductor. To achieve this improvement or to achieve high conduction capacity, we should add small amount of impurity to the pure form of semiconductor, that is intrinsic semiconductor. Okay, after then this semiconductor, after adding impurities, we get which semiconductor. That semiconductor is called impurity or intrinsic semiconductor, sorry, extrinsic semiconductor. That means after adding impurity to the semiconductor, that semiconductor is called extrinsic semiconductor, and the process of adding impurity to the semiconductor is called doping. Okay, the purpose of adding impurity is to increase either the number of free electrons or the or the hole in the semiconductor. That means the purpose of adding impurities is to increase free amount of free electrons inside semiconductor or number of free holes inside our semiconductor. There is two carriers of charge. One is electron and another is holes. Okay, so by adding some impurity, we can increase the number of electrons, free electrons, or the number of free holes. Okay, based on the impurity doped into the semiconductor, based on the type of impurity doped into the semiconductor, extrinsic semiconductor are two types. Okay, that means which type of impurity we added to the semiconductor, based on that the semiconductor is divided into, or the extrinsic semiconductor is divided into two types. One is N type, one is P type. Now let's see what is N type. Okay, when a small amount of pentavalent impurity is added to a pure semiconductor, it is known as N-type semiconductor. That means when we add pentavalent impurity to the semiconductor, that type of semiconductor is called N-type semiconductor. What is pentavalent? Pentavalent means the element which have 5 electrons in their outermost orbit. Okay, that is called pentavalent. That means 5 electron in valency band or valency stage. Okay, so the addition of pentavalent impurity provide a large number of free electrons in the semiconductor crystal. Okay, example of pentavalent impurities are arsenic, which atomic number is 33. Okay, and antimony, which atomic number is 51. Okay, let's consider one germanium silicon germanium semiconductor and arsenic impurity, which is pentavalent. Okay, in previous classes we germanium has 4 electrons in their outer orbit. Okay, and arsenic has 5 electrons, since it is a pentavalent impurity, 5 electrons in their outermost orbit. Okay, for in arsenic, in arsenic, 4 electrons share covalent bond with germanium. Okay, see, 4, 1, 2, 3, 4. But 1 electron is uh, ideally rested or don't participate in valence event, since there is no electron to share or participate with these with that electron. Okay, that means that this electron is free. So one arsenic atom, we get one free electron. If we add little amount of arsenic, then there is a millions of arsenic atoms and there is millions of free electron we get. Okay, that's why here it is tell that the addition of pentavalent impurity provide a large number of free electron in the semiconductor. Okay, such impurity which provide n-type semiconductor are known as donor impurity, because they don't donate or provide free electron to the semiconductor. This pentavalent impurity, or the impurity which create n-type semiconductor, that impurity is also called donor impurity. Okay, because they donate or provide free electrons to the semiconductor. Okay, next, this figure shows the energy band description of n-type semiconductor. The addition of pentavalent impurities has produced a number of conduction band. Okay, produce a number of conduction band electrons. That means free electrons, and that is free electrons. That means by adding pentavalent impurities, we get many conduction electron. The fifth leftover valency electron on the pentavalent atom cannot be accommodated in the valency band and travel to the conduction band. Which electron is left? The fifth electron. That means this electron is left out. So this electron is not staying in the valency band because this is free electron. Free electron stayed inside conduction band. Okay, the thermal energy of room temperature still generate a few whole electron pair. However, the number of free electron provided by the pentavalent impurity for excess the number of the holes, far exceeds the number of the holes. It is due to this predominance of the electron over hole that it is called n-type semiconductor. That means in n-type semiconductor there are two carriers, one is hole, one is electron, but the amount of electron is far much more than the amount of holes. So here the majority charge is electron and the minority charge is hole. Okay, because the dominance of electron over hole are more. Okay, now see n-type conductivity. In n-type conductivity, the current conduct in an n-type semiconductor is predominantly by free electron that is negatively charged and is called n-type or electron type conductivity. That means in n-type conductivity, majority charge or high amount of which charge carrier are there? Negatively charged carrier are there, which is electron. Okay, so the electron flow inside the uh, semiconductor is due to that electron or negatively charged particle. Okay, that's why this is called negative or n-type conductivity. Here when we apply what voltage, the in negative side, sorry, due to the positive side, the electron attracted towards positive and going through external or the flow of current, negative electron current is done. Okay, now see what is p-type semiconductor. Okay, when a small amount of trivalent means outermost have three electrons. Okay, the atom which have outermost, which have three electrons in their outermost, that electron is called trivalent impurity is added to a pure semiconductor. It is called p-type semiconductor. In n-type, pentavalent impurities are there or added. In p-type, trivalent impurities are added. Okay, the addition of trivalent impurity provide a large number of hole in the semiconductor. Well, okay, and the example of trivalent impurity is gallium and indium. Okay, such impurity which provide p-type semiconductor are known as acceptor impurity because the hole create can accept the electron. That means the which impurity or the trivalent impurity provided holes to the semiconductor and the hole accept electron. Since or due to these impurities are also called acceptor impurities. Here see gallium. Okay, here gallium is a trivalent means three electrons in their outermost. Germanium has four electrons in their outermost, so three electrons of gallium participate in covalent bond, but there is a vacant or missing electron, uh, or the hole created in another covalent bond. The hole which created, okay, and which created, that means one gallium atom provide one hole. Okay, so if we added small amount of impurity or trivalent impurity, then we get large amount of hole or positively charged particle in our semiconductor. Okay, and here the energy band diagram, valency band, due to the holes are there, these holes are stayed in valency band, and conduction band is nearly empty. Okay, and the conduction is, and the in p-type semiconductor the majority charge is hole because the amount of hole is much more than the amount of electrons in p-type semiconductor. So the majority charge carrier is hole and the minority charge carrier is electron. Okay, so here the current is flow due to the hole due to the hole. Okay, the current conduction in p-type semiconductor is predominated predominantly by hole, that is positively charged, and is called p-type or hole type conduction. Okay, here the negative side of the battery is attract holes. Okay, holes, and due to that the the flow current is done. Okay, thank you.